already discussed about the fundamental equations of thermodynamics. So the fundamental equation of thermodynamics is du equals to TdS minus PdV. So this is the fundamental equation of thermodynamics, and that represents the exact differential of the state function in internal energy U. And again we know that H equals to U plus PV, that is enthalpy equals to U plus PV. And if we do differentiate this equation 101, we can write dH equals to du plus PdV plus VdP. And again, by substituting this equation here, if we substitute this equation here, we can write dH equals to, that means you have to write this one TdS minus PdV in place of du. So if you write that, the equation will become dH equals to TdS minus PdV plus PdV plus VdP. That means PdV will be cancelled out, and simplifying that we will find out that dH equals to TdS plus VdP. And again, we know that the Helmholtz energy or the Helmholtz function A equals to U minus Ts. And again, differentiating this, you can write dA equals to du minus TdS minus SdT. Just differentiating this equation, you can write dA equals to du minus TdS minus SdT. And again, putting the value of du from the fundamental equation of state, we can write dA equals to TdS minus PdV minus TdS minus SdT. That means these two terms will be cancelled out. And finally, we can write dA equals to minus PdV minus SdT. So one equation we have find out that dH equals to TdS plus VdP, and the second equation we have find out that dA equals to minus PdV minus SdT. And similarly, if we solve the equation for using Gibbs energy or Gibbs function, we can write that can be easily solved dG equals to VdP minus SdT. Now from these relationship, we can find out the Maxwell's relationship or the Maxwell's functions. So if U is the state function, then the expression or fundamental equation for exact differential will become du equals to TdS minus PdV. And here internal energy is a function of entropy. From this equation, we can find out that internal energy is a function of entropy and volume. And similarly, if enthalpy is the state function, we can write dH equals to TdS plus PdV. And here we can write that enthalpy is a function of entropy and pressure. And similarly, so if we choose the state function A, we can write the differential equation, that is dA equals to minus PdV minus SdT. All these things we have derived in the previous section. And from this we can write Helmholtz free energy is a function of volume and temperature. And similarly, if we write G, if we consider the state function G, we can write the differential equation, that is dG equals to VdP minus SdT. And from this equation, you can see that Gibbs function or Gibbs energy is a function of pressure and temperature. Now, from these four fundamental equations of states, so these are the four fundamental equations of states, or these are the four fundamental equations for exact differentials. From these fundamental equations, we can derive the Maxwell's relationship. How we can derive? Just only one we will discuss. After that, easily in the similar method, you can do all these things. So the first fundamental equation is du equals to TdS minus PdV. Now, differentiating this equation with respect to entropy at constant volume. Again, I am telling, so this is the fundamental equation if we consider internal energy as the state function, and the fundamental equation is du equals to TdS minus PdV. And differentiating this equation with respect to entropy at constant volume, we can write del U by del S. We can write del U by del S at constant volume equals to T. How that will obtain? This PdP terms, if we will divide this TDS terms, so we can write del U by del S, differentiating this equation with respect to S. If we will differentiate this fundamental equation with respect to entropy, we can write that del U by del S at constant volume. This term will become derivative of TdS with respect to S, and that will become only T. And as the volume, as we have considered the volume as constant, so this term, the derivative of this term will become 0. So this is the first equation. We have find out that del U by del S at constant volume equals to T. And again differentiating this equation with respect to volume at constant entropy. So first you have differentiated that equation with respect to entropy at constant volume. You have find out this one, and after that again we will differentiate the same equation at constant. Again we will differentiate the equation with respect to volume at constant entropy. You can write del by del V. So the left hand side of this equation will become del by del V, del U by del S at constant volume, constant entropy equals to del T by del V at constant entropy. And in similar way, you can also, if you take the second equation, this one, similar way you will find two differential equations. The two differential equations are like this one and this one. And similarly, we will take the third equation, that is dH equal to TdS plus BTP. Exactly similar way it will differentiate twice. First, you have to differentiate with respect to P at constant entropy, you will get this equation. And after that, again, you will differentiate with respect to entropy at constant pressure, you will find out this. And after that, doing the similar differentiation for the rest two fundamental equations, you will find out the Maxwell relationship will be obtained like this. So there may be semester question derive the Maxwell's relationship, just like here one example is there. Derive the following expression for Maxwell relation using the Gibbs equation corresponding to Helmholtz function. So you have to derive this one. So this may be a 4 marks question. Now coming to Gibbs energy change for a reaction. Now if we consider the Gibbs energy change for any type of chemical reaction, so in that case you have to consider the standard Gibbs energy of formation of the compound, that is called del G F naught. The standard Gibbs energy of formation of a compound, that is called del G F naught, and that is defined as the Gibbs energy change taking place during the formation of the compound in its standard state from its constituent elements. Again, I am telling the definition of standard Gibbs energy formation of a compound del G F naught, that is defined as the Gibbs energy change taking place during formation of a compound in its standard state from its constituent elements in their respective standard states at constant temperature. So that is called del G F naught. And here, for any type of chemical equation, you can calculate the Gibbs energy change for a reaction, and that can be represented as a del G naught. So the del G naught equals to summation of Gibbs energy change of formation of compound, summation of del G F naught of the product minus summation of del G F naught of the reactant. So by using this equation, you can calculate the standard Gibbs energy change, that is called del G naught, for any type of chemical reaction. And the formula is just like this: del G naught equals to summation of del G F naught of the products minus summation of del G F naught of the reactants. And alternatively, you can also solve by using another equation, that is del G naught equals to del H naught minus T del S naught. And similarly, you can the question will arise: how can we calculate del H naught? Del H naught equals to summation of enthalpy of formation of the product minus summation of enthalpy of formation of the reactants. And similarly, del S naught equals to summation of standard entropy of the product minus summation of standard entropy of the reactants. So using these two, three formulae, we can solve numerical questions. So you can see this is a numerical question, and this type of questions. So that was a 5-mark question in last semester examination of June 2025. That is question number 7A. So here it is given, calculate the standard free energy change of the following reactions at 300 Kelvin using the data given below. So here the question is, so the chemical equation is given. So the chemical equation is just like this. Glucose, that is C6H12O6 solid, will undergo combustion C6H12O6 solid plus 6 oxygen gas, that will form 6 carbon dioxide gas plus 6 water vapor. So for this chemical equation, you have to calculate the standard energy change, and here the del G F naught of glucose is given here, del G F naught of carbon dioxide is given here, and del G F naught of water vapor is given here, or water liquid is given here. And for any type of elements, if that is not one compound, that is one element. Elements means that will form by a single atom. So here O2, similar type of atom or single atom, so that is a molecule formed by single atoms. So here this is oxygen molecule, so this is one element. So for the del G F naught of element is always considered to be 0. And here, so the question is, calculate the standard Gibbs energy change of the following reaction at 300 Kelvin using the data given below. And you can apply the formula we have just studied, that is del G naught equals to summation of del G F naught of the product minus summation of del G F naught of the reactant. So in this equation, the products are carbon dioxide gas and water liquid. So these are the products, and the del G F naught values of the products are given, and also the del G F naught values of the reactants are given. So first you calculate the del G F naught values of the reactant minus del G F naught values of the product. So one error is there. So here the question can be solved like this: del G naught equals to del G F naught values of the product minus del G F naught values of the reactant. So that means so here this is the del G F naught values of the reactants. So from the table you can find out for C6H12O6 the del G F naught value is minus 913 kilojoule per mole. Just you, so that is del G F naught values of C6H12O6 plus del G F naught values of 6 oxygen molecules. 6 oxygen molecules are there. So as oxygen is one element, so the del G F naught values of oxygen is 0. So the final value of del G F naught of the reactants equals to minus 913 kilojoule per mole. And similarly, the del G F naught values of the products you can calculate by using this table. So that is 6 into minus 395. So 6 into minus 395 plus 6 into minus 237 plus 6 into minus 237. So the final value will be minus 3792 kilojoule per mole, and hence the del G naught value equals to del G F naught value of the product minus del G F naught value of the reactant. So individually here we have calculated the del G F naught values of the product and del G F naught values of the reactant, and after that we just put that. So this is the del G F naught values of the product minus del G F naught values of the reactant, and finally you can write this. So this is a 4-mark question in the last semester. But here in the question, so this equation was not there. So the equation was changed. The equation was N2O gas plus 3 hydrogen gas, that will give rise to N2H4 gas plus water liquid. So, and the table values of del G F naught values were given. So just you have to calculate using this equation. And here another question is there. Calculate the standard free energy change of the following reaction at 300 Kelvin from the given data. So here del G F naught values are not there, but del H F naught values are there, and S naught values are there. Entropy, standard entropy values are there, and standard enthalpy of formation values are there. So you can use the second equation, that is del G naught equals to del H naught minus T del H naught. So the del H naught, first you have to calculate this one, del H naught, and again the formula is like this: del H naught equals to enthalpy of formation, standard enthalpy of formation of the product minus standard enthalpy of formation of the reactant. So here the product is ammonia gas and the reaction is nitrogen gas plus hydrogen gas. So you can write del H naught equals to 2 into del H F naught of ammonia minus del H F naught of nitrogen gas plus 3 into del H F naught value of hydrogen gas. So by putting all the things, you can write, you can So exactly similar type of numerical questions will come in your semester examination, and if you solve all the questions given in your study material, you can easily appear for semester examination. Now coming to the next part. The next part is system of variable composition, and I think in the last examination all the questions 11 marks questions were there from the first part, and no questions were there from the second part. So definitely for the next coming examination, question may come from this part, second part. So the second part is partial molar quantities and their significance. So here we will discuss what is partial molar quantities. Now coming to effect of change in the composition of the system of the thermodynamic properties of the system. Effect of change in, so the partial molar quantities can be understood by using effect of change in thermodynamic, effect of change in composition of the system on the thermodynamic properties of the system. That means if you will change composition of the system, then what type of change will be observed in the different thermodynamic properties. Different thermodynamic properties means just like enthalpy, entropy, or free energy, Gibbs free energy, or Gibbs energy, Helmholtz energy, etc. So what type of change will arise in the thermodynamic functions like enthalpy, entropy, Gibbs energy, Helmholtz energy, etc. As you have already studied the composition of a system comes into picture only when the system consists more than one substance. So if the system consists a single substance, then the composition is 100%. But if the system contains more than one substance, so then if the system contains more than one
हेलो, क्लासेस नहीं चल रही क्या?
हाँ सर, नहीं सुनाई दे रहा है कुछ भी।
जी?
सर हैज लेफ्ट, आई थिंक सो।
जी एक्चुअली आपका आवाज नहीं आ रहा है, थोड़ा जोर से बोलेंगे तो।
सर हैज लेफ्ट, आई थिंक सो।
हेलो, क्लासेस नहीं चल रही क्या?
शायद नहीं, मतलब सर नहीं है क्लास में।
आपने कल ज्वाइन किया था क्या?
हाँ किया था।
कल क्लास हुआ था?
कल तो दूसरे मैम का हुआ था।
मतलब ये जो 6 से।
इनऑर्गेनिक
ओके,
इनऑर्गेनिक हुआ था आज। आज से फिजिकल हो रहा है।
कल 6 से 7 हुआ था क्या?
नहीं, 6 से 8 ही था, पौने 8। लेकिन
जी जी।
इनऑर्गेनिक केमिस्ट्री था।
ओके, कल हुआ था पर आज 6 से शुरू नहीं हुआ क्या कोई क्लास?
नहीं, 6 से शुरू हुआ था तो
फिर
अभी
अभी
5 मिनट पहले ही शायद कुछ सर का मतलब नेटवर्क इश्यू होगा, इसीलिए नहीं ज्वाइन कर रहे हैं।
ओके, तो फिर रहना पड़ेगा इधर। ओके देन।
हम्म। Can anybody tell me that the assignment submission date has been postponed?
आई थिंक नो।
It's
Yeah,
30th
so
September only, no?
there was an update. So I think 15th to 30th September if we go physically and submit, up
Okay.
to 10th October if we send by speed post. That's the last
Okay.
update I got. Yeah,
Acha, acha. Okay, okay. Thank you.
Yes, yes.
no problems, no problems.
Actually, where are you guys writing your assignments?
I didn't get you. Like, we are submitting
नहीं,
it.
नो आई एम एक्चुअली आस्किंग दैट आप असाइनमेंट कहाँ से लिख रहे हैं?
कहाँ से मैंने हाँ ऐसे कुछ मतलब खरीद के
जो
मिलता है असाइनमेंट. So I have bought it and then I'm going to. I've not yet started. I've only started the math assignment. और दूसरा जो assignments I have to still study and then I'll be seeing it from the. I'll be referring it to the assignments which I've bought it. और फिर जो हमारा स्टडी मटेरियल है उसी में से लिखूंगी.
actually I have no idea about how to write an assignment like that. So uh, could you share the details of that from which you have purchased or something like that?
Yeah, I'll try to send one assignment. But where
Okay.
should I send it?
Okay. Can
And
we
which
guys
number?
can we sorry?
Like where should I send it? Where should?
Uh, Actually you can send me in my number if you
Yeah,
want
please
to.
give me a number.
8917
8917
44
44
right
hmm?
0158
0158
right 8917
hmm?
44
Hmm?
0158.
58. And your name is Bishwajit.
Yeah, right. I think you're okay.
Ratna.
Yeah, I got you. I got you.
You have downloaded. Okay. Sir has come.
Hello.
Yes, sir. Yes, sir.
Hello.
You are audible.
Yes,
Yes,
sir.
sir.
Okay, actually some network problem are there.
Okay, sir.
So we will start from the partial molar property. Okay. So here, the partial molar properties are the extensive thermodynamic properties. Here the extensive
Sir, you are not at all audible, sir. Hello? Could you hear me, sir? You are not audible, sir.
thermodynamic properties
Sir, we cannot hear you.
are volume, internal energy, enthalpy, velocity, and
Yes, sir. Yes, sir. Now you are audible.
Okay, okay. Okay, the screen is visible.
Yes, sir. Right
Okay.
now it is visible.
So here we will discuss about thermodynamic properties or extensive properties are the properties which are dependent upon the amount of substance present in the system. So these are called extensive thermodynamic properties. Just like volume is also dependent upon the amount of the substance present in the system, internal energy, enthalpy, Helmholtz energy, Gibbs energy, all these are called extensive thermodynamic properties. And what are intensive thermodynamic properties? So intensive thermodynamic properties are the properties which are independent upon the amount of substance present in the system. For like temperature, if you take 10 ml of water, you know, you will take 10 ml of water on your laboratory table and in another vessel 50 ml of water. So for both the system, the temperature is same. So that is independent upon the amount of the substance present in the system. So temperature, external pressure, refractive index, dielectric constant, all these are intense molarity, all these are intensive thermodynamic properties. But extensive thermodynamic properties are volume, internal energy, volume V, internal energy U, enthalpy H, Helmholtz energy A, and Gibbs energy G. So these are extensive thermodynamic properties. So here we will discuss that for multi-component system, if you will change the composition of any system, what will happen to the values of extensive thermodynamic properties, that is called partial molar properties. So here, for all extensive thermodynamic properties like V, U, H, A, or G, you can take the partial molar property, the value of the molar value will be represented as X. So xm equals to x by n, xm equals to x by m. X means value of the thermodynamic properties of the system. You can take any extensive thermodynamic property just like volume or internal energy or enthalpy or Helmholtz energy or Gibbs energy divided by amount of the system in number of moles. So you may note that if we use this formula for volume, the molar volume Vm equals to V divided by N. V is the total volume of the system divided by number of moles, that will become molar volume. And similarly, if we use this equation for internal energy, you will get molar internal energy. This equation for enthalpy, you will get molar enthalpy, molar Helmholtz energy, molar Gibbs energy, etc. So let us write the mathematical expression for the change of thermodynamic property X with change in composition of the system. That means particularly this is applicable for multi-component system, because for multi-component system you can change the composition. If single component system is there, the composition is 100%. There will be no change in composition. For multi-component system, that may be two component, maybe three component, etc. For multi-component system, you can change the composition of any one component or more. So let us write the mathematical expression for the change of thermodynamic properties like V, U, H, A or G. So generally that is represented as X with change in composition of the system. And already two independent thermodynamic variable were there, that is temperature and pressure. And for multi-component system, another variable will arise, that is the composition. So here X is completely dependent upon temperature, pressure and composition for multi-component system. For single component system, there will be no composition variable. X means any thermodynamic property like V or U or H or A or G. So X is a function of T, P, N. T means absolute temperature, P is the external pressure and N is the number of moles. So here X is said to be a dependent variable which depends upon the values of T, P and N, which can be varied independent of each other and are called independent variables. We can take the case where we keep two variables, say pressure and number of moles constant, and vary the temperature. So here three variables are there for multi-component system, that is temperature, pressure and number of moles N. So we can change the fractionally the value of X if we'll change any one variable. So here we have taken the example, we keep two variables like pressure and number of moles as constant and vary one of the variable like temperature. So this will bring in change in the property, that is the extensive thermodynamic property. We can change pressure or number of moles keeping. Similarly, we can change pressure or number of moles keeping temperature and number of moles constant, or temperature. That means you can change pressure keeping temperature and number of moles constant, and also you can change number of moles keeping temperature and pressure constant respectively. So here X is a function of temperature, pressure and number of moles. Now taking the differential form from this equation 2.8, we can write the equation 2.9 like this: dx equals to, so here this is the differential form of equation 2.8. You can write dx equals to del x by del t at constant pressure and number of moles dt plus del x by del p at constant temperature and number of moles dp plus del x by del n at constant temperature and pressure dn. So here in the first term we have changed the value of temperature keeping the value of pressure and number of moles constant. In the second term we have changed the value of pressure keeping the value of temperature and number of moles constant. In the third term we have changed the value of temperature and pressure keeping, in the third term we have changed the value of number of moles keeping temperature and pressure constant. So all these individual terms are called partial changes. So the differential in the first term of the right hand side, represent the change in property of X when temperature of the system is changed, keeping pressure and N constant. That means the first term. And similarly, the second term represent the change in property X as a function of temperature, keeping the second term represent the change in the value of X when pressure changes, keeping temperature and number of moles constant. Similarly, the third term, the value of change in the value of X with change in the value of N, keeping temperature and pressure constant. So here if there will be so if we use this equation or this expression for a binary system, let us extend the argument to a binary mixture where Na is the number of moles of component A and Nb is the number of moles of the component B, and work out the corresponding expression of change in property X. So if you argument by so this is the change in x for a single system, but here this is the change in the value of x for a binary system. So the binary system will form by taking Na moles of A plus Nb moles of B. So for this binary system, x is a function of temperature, pressure, number of moles of A and number of moles of B. So here x was a function of T, P and N, but here x is a function of T, P, Na and Nb because this is a binary mixture. So if you use the same differential from this binary mixture, so dx equals to del x by del t. That means individually you have to take the partial derivative term keeping all the other three terms constant. So here, so this is the change in value of x with respect to change in temperature, keeping pressure Na and Nb constant. The second term is the change in value of x with respect to change in pressure, keeping temperature Na and Nb. So here one printing mistake is there. You have to write T here, not P. You have to write T here. You can see in the second term, one printing mistake is there. In place of P, you have to write T. So the second term represent the change in value of x with respect to change in pressure, keeping temperature Na and Nb constant. The third term represents change in value of x with respect to change in number of moles of A, keeping keeping temperature, pressure, and number of moles of B constant. And the fourth term represents change in value of x with respect to change in number of moles of B, keeping temperature, pressure, and Na constant. So this is the differential form for a binary mixture. And you can note that the thermodynamic property X changes with change in temperature, pressure, Na and Nb. Now, if we wish to know the change in property on changing Na and Nb while keeping temperature and pressure constant. So from this equation, generally we know that whenever we are doing any type of experiment in the laboratory, that means in open system, the temperature and pressure are constant. So for open system, the temperature and pressure are constant. The first two terms will be cancelled out. dt will be 0 and dp will be 0. So the first two terms will become 0. The second term will become 0. So at constant temperature and pressure, the equation 2.11 will become like this: dx equals to del x by del Na Tp Nb constant dNa plus del x by del Nb dNb at constant Tp Na. So these two terms, the first term, this one, at constant temperature and pressure, the first and second term will be cancelled out because both the terms will become 0 at constant temperature and pressure. That means for open system, while we are doing any type of experiment in the laboratory, we are performing the experiment at constant temperature and pressure. So the two terms will be cancelled. Only we will consider the third and fourth term. So the equation will become dx equals to del x by del Na dNa at constant Tpnb plus del x by del Nb dNb at constant Tpna. Now, for equation 2.12, these term, first term and the second term, are the partial derivative property with respect to number of moles of the component Na and Nb. That means this one is the partial derivative property with respect to number of moles of A, and this term the partial derivative property with respect to number of moles of B. Partial derivative property means if you will take internal energy, that is the partial derivative internal energy. If you will take enthalpy, that is the partial derivative enthalpy, like this. So these terms are known as partial molar properties. That means the first and second term of equation 2.12. So both the terms are called partial molar properties. So that is del X by del Na at constant temperature, pressure, number of moles of B represent the partial molar property of the component A, and similarly del X by del Nb at constant temperature, pressure, number of moles of A will represent the partial molar property of the component B. Now, to understand the physical significance in terms of partial molar property, let us consider the situation where we will take a large volume of the binary mixture and add 1 mole of component. So here we have taken a large volume of a binary mixture A plus B. To that system, we have to add 1 mole of component A. That means you have to add, that means you have changed only the number of moles of A, keeping the number of moles of B constant. So here we have added 1 mole of the component A to it, that is, and hence as we have added only 1 mole of the component A, only component A, any substance of B, we have added 1 mole of component A. So the change in number of moles of A, that is DNA, equals to 1. Since we have taken a large volume, the mole fraction of the component B practically does not change, that is DNB will become 0. As we have taken large, suppose we have taken 1000 moles of A and B, and to that system we have added just 1 mole of component A. So the mole fraction of the component B, that is DNB, will not approximately change, and hence substituting the value in this equation 2.12. So here DNA equals to 1 and DNB will be equals to 0. So the equation 2.12 will change into like this: dx equals to del X by del Na at constant temperature, pressure, and number of moles of B. So thus partial molar property of component A in a mixture can be defined as the change in the change in the property X of the mixture when 1 mole of component A is added to a large volume of mixture at constant temperature and pressure, keeping the amount of the remaining component constant. So here you have added only 1 mole of component A at constant temperature and pressure. Initially we have considered at constant temperature and pressure, keeping the number of moles of the remaining constant, keeping the number of moles of the remaining components at constant. So the change in the partial change in the value of X is called partial molar property. So this is the definition of partial molar property. And the partial molar properties can be represented as XIM or XI bar, where I represent the component whose amount is being changed, and the subscript M or bar on the top of the symbol of the property indicates the property to be molar. So if M is there, that means the property is for molar property, or that can be represented as X bar or XM like this. And I represent the component whose amount is being changed. So using such representation, if we use this type of, that means if we use this type of representation, then the equation 2.12, this one, if we use this type of representation in equation 2.12, so the equation 2.12, this one, so that means here you have to put the value as XM. XAM. So here so this is the A, the component is A, and here we have to put dx equals to XAM DNA plus XBM DNB. Here dx is the total change in property X due to change in composition at constant temperature and pressure. Now if we apply what we have discussed here in terms of X, the X may be any type of extensive thermodynamic property. So if we will put volume in place of X, so that is called partial molar volume, and that is represented as del V by del Ni at constant T, P, Nj. and if you put internal energy in place of X, that is called partial molar internal energy. If we put enthalpy in place of H, that is called partial molar enthalpy. If we put entropy in place of S, that is called partial molar entropy. If we put Gibbs energy in place of X, that is called partial molar Gibbs energy. And the other name of partial molar Gibbs energy, that is called chemical potential. Partial molar Gibbs energy is also called as chemical potential. In the previous part, we have discussed taking X as a general extensive thermodynamic properties, and we have find out the partial molar property as XIM, the partial molar property as XIM, where I is the I, where I is the component whose amount is being varied, and M is the subscript used for molar property. So that's why XIM is called partial molar property. And if you will use internal energy, if you will use volume, that can be represented as VIM or VI bar, that is called partial molar volume. If you will use internal energy, that can be represented as UIM or UI bar, that is called partial molar internal energy. If you will use enthalpy, that is called that can be represented as HIM or HI bar, that is called partial molar enthalpy. If you will use entropy, that is called SIM or SI bar, that is called partial molar entropy. If you will use Gibbs energy in place of X, that is called that can be represented as GIM or GI bar, that is called partial molar Gibbs energy, and the other name of partial molar Gibbs energy is called chemical potential. Now, if we extend the argument to multi-component, so here we have in this derivation section, you can see initially we have considered the partial molar property. Initially, we have taken only one component, that is change in thermodynamic property, change in extensive thermodynamic property with respect to change in amount of that component. And we have used the same argument to binary system or two component system. And after that, here we will use the same argument to a multi-component system. And later the multi-component system is formed by mixing of Na moles of A, Nb moles of B, Nc moles of C, and so on. So the extensive thermodynamic properties can be represented as X equals to function of temperature, pressure, Na, Nb, dot dot. If you take differential of this equation 2.15, that will become dx equals to del x by del t dt at constant pressure, Na, Nb, and so on, plus del x by del p dp at constant. So here you have to again one printing mistake is there, you have to write t here. So del x by del p at constant temperature, Na, Nb, and so on, plus del x by del Na at constant temperature, pressure, Nb, Nc, and so on. Del x by del Nb dNb at constant temperature, pressure, Na, Nc, and so on. And the last one may be del x by del Ni dNi at constant temperature, pressure, number of moles of A, number of moles of B, so on. So here the similar expression here we have applied for multi-component system. So under the condition of constant temperature and pressure, this term will become 0, and again this term will become 0. So at constant temperature and pressure, the value of dx can be written like this, taking the first two terms 0, and using the representation of partial molar quantities, the dx can be represented as dx equals to xam dna plus xbm dnb plus dot dot plus xim dni. After that, the relationship between thermodynamic property and partial molar property. So here, so we will continue the discussion after 2-3 minutes of break. I will take 2-3 minutes of break. After that, again we will continue. So again we will resume the section. So here we will discuss the relationship between thermodynamic property and partial molar property. Here in the previous part we have already discussed, if you consider a binary mixture, the mole fraction of component A, the mole fraction of component A in a mixture containing Na moles of A and Nb moles of B is, what is the mole fraction? Chi A equals to number of moles of A divided by total number of moles, that is Na divided by Na plus Nb, which is equals to Na divided by N. N means total number of moles, and hence Na equals to Chi A into total number of moles. And here N is equals to the sum of the sum of the number of moles of A and B. And similarly for the component B, we can write Nb equals to NB equals to chi B into total number of moles. Whether the screen is visible or not? Hello?
Yes, sir. Yes.
Yes, sir, it is visible.
Yes, sir.
So here we can write Na equals to number of moles of A equals to mole fraction of A into total number of moles, and similarly NB equals to number of moles of B, NB equals to mole fraction of B into total number of moles. To keep the composition of the mixture constant, that is Na and Nb should be changed in such a way that chi A and chi B do not change. Let us increase the total number of amount of A and B. So that means here we have to change the number of moles of A and number of moles of B, so that there will be no change in mole fraction of A and mole fraction of B. That means simultaneously you will add number of moles of A and number of moles of B. So that is, let us increase the total amount of A and B. Just wait 1 minute. So here, let us increase the total amount of A and B from n moles to kn moles. So initially the total number of moles was n mole, where Na moles of A was there and Nb moles of B was there. And now the total number of moles will be increased to Kn, maintaining the mole fraction of the two component constant, maintaining the mole fraction of the two components constant. If we represent the number of moles, if we represent the number of moles of A as DNA and the change in number of moles of B as DNB, so that is DNA equals to chi A into DN, DNB equals to chi B into DN. So DN equals to, DN means change in number of moles. Initially the total number of moles was N, and finally the number of moles was Kn. So change in total number of moles Dn equals to Kn minus N, that is equals to N whole into K minus A. So here chi A and chi B are not changing, or we change the simultaneously we will change both the amount of A and B. Now substituting the value of DNA and DNB in the previous equation 14, so this was the previous equation 2.14, this was putting the value of DNA and DNB in equation 14. We can write dx equals to xam into chi A dn plus xbm into chi B dn. So that is equation 24. Now integrating the equation 2.24, integrating the equation 24, taking the limits. Here the initial number of moles was n and the final number of moles was kn, and the initial thermodynamic property was x and the final thermodynamic property was kx. So just integrating this equation, we can write integration of dx equals to integration of dx from x to kx equals to whole integration of xam chi A plus xbm chi B dn from n to kn. So this is equation 25. And again you should remember that these values have changed the composition in such a way that the mole fraction of the two components do not change. That means simultaneously we have changed the composition of A and B simultaneously, so that the mole fraction of A, that is chi A, will not change, and also the mole fraction of B, that is chi B, will not change. So, solving the integration part in the LHS, you can see that is kx minus x equals to xam chi A plus xbm chi B into integration of dn from n to kn. Now simplifying this one, we can write x whole into k minus 1 equals to xam chi A plus xbm chi B whole into k minus 1 n. Now putting the values of xa and xb and simplifying, you have to simplify that one. After putting the values of xa and xb, after putting the value of chi A and chi B, putting the value of chi A and chi B, we can write x equals to xam Na plus xbm nb. So this is the desired relationship between the thermodynamic property and the partial molar property and the partial molar properties of the component in a binary mixture. So this is the relationship, and the question may be like this: derive the relationship between the thermodynamic property and the partial molar property. So after that, we will discuss the partial molar volume, particularly partial molar volume. So here we have to take volume in place of x. So the volume of a binary solution which is dependent upon the temperature, pressure. So if we are considering a binary solution, so volume is a function of temperature, volume is a function of temperature, pressure, and number of moles of A, number of moles of B, etc. So that is equation 30. So this is equation 30. So volume is a function of temperature, pressure, number of moles of A and number of moles of B. And using equation 12, we can write the expression for change in total volume of the binary mixture with change in amount of the component A and B at constant temperature and constant pressure, that is dV equals to, so the equation 12 was for x. So here in place of x, we are just writing V. You can see equation 12, 2.12, this one. So this is the equation 12, that is for x. So here in place of x, we are using volume as the extensive thermodynamic function. So putting the value of x as v, we can just write dv equals to del v by del na dna at constant temperature, pressure nb plus del v by del nb dnb at constant temperature, pressure and na. So here the first term of this equation 31, this term of equation 31 is called partial molar volume of A, and the second term, this term of equation 31 is called partial molar volume B. Now so that means we have derived exactly same type of expression using x, and here in place of x we are taking v. So if we will take the in place of x, if we will take v, then that is called partial molar volume. Now suppose we will add 1 mole of component A to the mixture of at constant temperature and pressure, maintaining the number of moles of B constant. In such case, DNA equals to 1, and hence the first term DNA equals to 1, and hence and DNB equals to 0, because maintaining constant B, the second term will become 0. So dV equals to del V by del Na. That so the equation 31 will converted to dV equals to del V by del Na at constant temperature, pressure and Nb. This is called partial molar volume. Exactly similar type of expression we have calculated using x, that is dx equals to del x by del Na T P Nb constant. So here in place of x we are putting the value of V, So that this is the mathematical definition of partial molar volume. And similarly, in place of x, we have taken the value of d. So we have taken the value of volume here. So we can write dV equals to VAB dNA plus VBM. dV equals to VAM dNA plus VBM dNB. And again, that value can be written as V equals to VMA NA plus VMB NB. Now coming to partial a physical insight of the partial molar volume. So this is the partial molar volume VMB equals to del V by del NB at constant temperature, pressure and number of moles of A. So here one question is there. You can solve easily putting all the values. So all the values are here given. So you can calculate the value of Na, calculate the value of Nb, and after that calculate the value of Xb. And similarly, this is for you have to calculate the change for a large change. The value of VMB equals to del V by del Nb at constant temperature, pressure and number of moles of A. So here one numerical question is there. The partial molar volume of water and methanol in a solution having 5.53 mole of water, 2.45 mole of methanol at 298 Kelvin, 1 bar of pressure are 17.74 centimeter cube per mole, 38.8 centimeter cube per mole respectively. Calculate the total volume of the solution. Just you have to put this equation V equals to V mw nw, W means water, and plus V nm, capital M means methanol. So here Nw is given, Nm number of moles of water is given, number of moles of methanol is given in the question, and Vmw is given, Vmm is given. Substituting all the values, you can solve the question. All of you should go through the numerical questions what are given in your study material. Now coming to volume of mixing, del V mix, that is called volume of mixing. So the volume of mixing, that is del V mix, equals to VAM Na plus VBM NB minus VAM Na, V star AM Na plus V star BM NB. So V star AM and V star BM are the molar volume of pure component A and pure component B respectively. So here the molar volume of the pure component A and pure component B are taken in bracket, and the sum of the values of the pure component A and pure component B are taken in bracket here. So here, if we are considering a ideal solution, V equals to this one, and hence for ideal solution del V mix is 0, but for non-ideal solution this value is not equal, so that the del V mix is not equal to 0. This is for non-ideal solution. So here as these are not equal, so the del V mix are not equal to 0. Now after that the experimental determination of partial molar volume. So in the experimental determination of partial molar volume, so that is applicable for non-ideal binary solution. So for non-ideal binary solution del V mix is not equal to 0, but for ideal binary solution del V mix equals to 0. By using a linear graph, you can calculate the partial molar volume experimentally. Now coming to partial molar free energy. So this one is very important part. The partial molar free energy, that is called chemical potential. Partial molar Gibbs energy. Partial molar Gibbs energy, that is called chemical potential. So the partial molar Gibbs energy, the partial molar Gibbs energy are also important in study the chemical equilibrium, phase equilibrium. Due to the importance of partial molar Gibbs energy in thermodynamic studies, it was given a special name chemical potential. So a Again, I am telling partial molar Gibbs energies are important in thermodynamics to carry out or to know the state of chemical equilibrium or to know the state of phase equilibrium. So due to its importance, it is given another name that is called chemical potential. So now the chemical potential is nothing but that is the partial molar Gibbs energy, and that the expression of the partial molar Gibbs energy is like this: del G by del Ni at constant temperature, constant pressure, and constant number of moles of remaining term. Remaining term means except the ith term at constant number of moles of the remaining term, that is represented as Nz. So that is called partial molar free energy, partial molar Gibbs energy. So the partial molar Gibbs energy, its other name is chemical potential, and it is represented by a symbol mu. So the partial molar Gibbs energy or chemical potential is represented as mu, and the mu for the ith component can be represented as mu I equals to del G by del Ni at constant temperature, pressure, and constant number of moles of remaining components. Here you exactly in the similar way we will derive the value of partial molar Gibbs energy. We know that the Gibbs energy is a function of temperature, pressure, number of moles of A and number of moles of B for a binary component or for a binary solution formed by mixing Na moles of A and Nb moles of B. So the so the Gibbs energy is a function of T, P, Na and Nb. Now using the differential of this equation, we can write dg equals to del G by del T dt at constant pressure, constant Na, constant Nb, plus del G by del P dP at constant temperature, constant Na, constant Nb, plus del G by del Na dNa at constant temperature, constant pressure, constant Nb, plus del G by del Nb at constant temperature, constant pressure, constant Na dNb. And again, from the previous section, we know that del G by del T at constant pressure, constant Na, constant Nb is nothing but that is minus S, and del G by del P at constant temperature, constant Na, constant B equals to V. Now, and similarly, this term is called chemical potential of component A, that is mu A, and this term is called chemical potential of component B, that is mu B. Now putting all these values in the above equation 50, putting all these values in the above equation 50, we can write dg equals to minus sdt plus vdp plus mu A dNa plus mu B dNb. And if we will consider the temperature and pressure as constant, that means if you will do the experiment in your laboratory, the temperature pressure as constant, that means in an open system the temperature pressure are constant. So dt equals to 0 and dp equals to 0. So this term will become 0. The second term will also become 0. So we can write dg equals to mu A dNa plus mu B dNb. This expression gives the change in Gibbs energy with change in the composition of a binary mixture at constant temperature and pressure. Using the equation 28 and replacing the value of x by g, the total Gibbs energy of the binary mixture can be written as g equals to mu A Na plus mu B Nb. Now this gives the total Gibbs energy of a binary mixture at a fixed temperature, fixed pressure, and fixed composition. And again, for a pure component, if there will be only one component A will be there, so G equals to mu A plus Na, and similarly mu A equals to G divided by Na. So this expression implies that the chemical component of a pure substance is equals to molar Gibbs free energy of the substance. Now that is called the chemical potential of component A, that is mu A. Now coming to the significance of chemical potential. So the So here this is the significance of chemical potential. The chemical potential can be seen as the escaping tendency of a substance in a mixture. That means the molecules of a component spontaneously move from one region to another. So region with high chemical potential, so region to the low chemical potential region in a mixture. That means so the component will spontaneously move from high chemical potential region to low chemical potential so region till the chemical potential of both the region will become same. For example, if we add a drop of ink in water taken in a beaker, then the molecules of ink in the region of drop gradually but spontaneously spread out. So that is the physical significance. So this is the molecule of the ink. So that will continuously spread out until all the chemical potential of all the throughout the system will become same. Now coming to effect of temperature and pressure on chemical potential. First we will discuss the effect of temperature on chemical potential. So the chemical potential is nothing but the chemical potential of ith component is mu I, that is equals to del G by del Ni at constant temperature, pressure and constant number of moles of remaining component, that is Nj. So this is the chemical potential of the ith component. Now differentiate, so this is equation 48. Differentiating the expression with respect to temperature, keeping the pressure and composition constant, we can write del mu I by del T at constant P Ni Nj equals to del by del T del G by del Ni at constant T P Nj and constant P Ni Nj. Now using the Euler's relationship, we can write this one equals to minus S. Therefore, the overall equation can be represented like this. And here, so that is the definition of partial molar property. You can apply the definition of partial molar property. So that is del S by del Ni at constant temperature, pressure and constant remaining number of moles, that is called SIM. So this is another partial molar property, that is called entropy, that is SIM. Now putting the values, we can and solving the equation, we can write, simplifying that, we can write mu I T2P. So here we are deriving the effect of change in chemical potential with change in temperature, and hence the temperature will changes from T1 to T2 at constant pressure. So mu I T2P minus mu I T1P, that means the temperature changes from T1 to T2 maintaining constant pressure. So what will happen to the chemical potential of the ith component? So solving this, we can find out the mu I chemical potential of ith component at temperature T2, constant pressure P, minus mu I, that is chemical component of the ith component at temperature T1 with constant pressure P, equals to minus SIM dt from T1 to T2. And similarly, this is the effect of change of pressure on chemical potential. And you can see here, this is the effect of change of pressure of the chemical potential, that is d mu I equals to, so if we will change the effect of change of pressure at constant temperature of chemical potential, the entropy will remain constant, so only the volume term will be there. So d mu I equals to Vim dp. Now coming to, if we will apply this principle to a mixture of gases, so the chemical potential of a pure substance is similar to Gibbs molar Gibbs energy. And further, if you recall the previous unit, that Gibbs energy change for a pure substance, we know that for a pure substance, Dg equals to minus SdT plus Vdp. Now combining both the equations, we can write d mu I equals to minus SIM dt plus Vim dp. And again, for a pure substance at constant temperature, the above equation becomes du equals to Vm dp, and taking integration of the both the equations at constant temperature and variable pressure from P1 to P2, we can write this expression And finally, solving this, we can write mu at constant temperature and pressure equals to mu naught at constant temperature equals to Vm P minus 1. And here this is the chemical potential of ideal gas in terms of pressure. Okay, so here we will so here this is the chemical potential of ideal gas in terms of pressure. Ideal gas, so for ideal gas we should use the term pressure, but in case of real gases, the chemical potentials of a real gases can be used. So for real gases, in place of pressure we are using the fugacity. So in the above real gases, the pressure is replaced by the term fugacity. And again, we know that the relationship between fugacity and pressure, F equals to gamma P. Here gamma is known as the fugacity constant, whose value is equals to 1 for an ideal gas. That means for ideal gas, fugacity F equals to P. So that's why for ideal gas, we are using the term pressure. But for real gas, the pressure cannot be applied. You have to use the term fugacity. So F equals to gamma P. Gamma is nothing but the fugacity constant. So by using gamma P in place by using fugacity in place of pressure, the above equation can be written like this. So the next is Gibbs Duhem equation. This one is the most expected question for this semester examination because in the last year means in the last semester, partial molar volume was there, another question, 2 marks question, and partial molecular expression of partial molar free energy was there. So Gibbs Duhem equation was the is the very important question. So in order to derive this equation, you have to consider equation 24. Equation 24 is dx equals to xma dna plus xmb dnb. All these equations we have derived in the partial molar property section, and where the total extensive property at a given temperature and given pressure and given composition is given by equation 28. So the 28 was represented like this: x equals to xma na plus xbm nb. You remember this was equation 24. Dx equals to xma dna plus xmb dnb, and equation 28 was like this: x equals to xma na plus xmb nb. The differential form of equation 28 will become, so if you will take the differential form of this equation 28, if you will use the differential form of equation 28, we can write the differential form of this equation 28, we can write dx equals to, keeping this one constant, we are taking the differential of this one, and the second term is like this: keeping this one constant, we will take the differential of first one. So the differential term, the differential equation will be taking differential of equation 28, that can be converted into 88 like this: dx equals to xma plus dna plus na dxma plus xmb dnb plus nb dxmb. Now if we will compare equation 24 and equation 28, here you can see this is equation 24 and here this is equation 28. If we will compare both these equations, just you can see, if we will compare both these equations, in the RHS of equation 24, you observe RHS of equation 24, both the terms were there, is there here: xma dna plus xmb dnb. So both the terms are here: xma dna plus xmb dnb. That means the addition of both the terms will become 0. If we compare equation 24 and 28, you can write na dxma plus nb dxmb equals to 0. This is known as Gibbs-Duhem equation. This is the Gibbs-Duhem equation. So this is the derivation of Gibbs-Duhem equation. That may be a 4-mark question. So the Gibbs-Duhem equation can be written in terms of volume. So here X is any thermodynamic extensive property. If you write the Gibbs-Duhem equation in terms of volume, that equation can be written as Na dVma plus Nb dVmb equals to 0, or Na dVma equals to minus Nb dVnb. And if you write the Gibbs-Duhem equation in terms of chemical potential, that can be written as Na d mu A plus Nb d mu V equals to 0. And if changes in temperature and pressure are also considered, then that means till now we have taking the expression at constant temperature and constant pressure. But if changes in temperature and pressure are also considered, then the Gibbs-Duhem equation in terms of chemical potential can be written as minus SdT plus VdP. So that means if temperature and pressure change is considered, both the terms will not become 0. So the equation will be like this: minus SdT plus VdP plus Na d mu A plus Nb d mu V equals to 0. So here two questions are there. For a binary mixture where Na equals to 3 Nb, if the chemical potential of A changes by 2 joule per mole, what is the change in chemical potential of B? So just you have to solve this equation by using equation 92. So you have to solve this question by using equation 92. And similarly, this is another question, similar type of question is there. So all these are term end questions. You have to solve these questions. You go through all these questions and also all the examples. Then you can easily secure more marks in your semester examination. So till now we have completed the thermodynamics part, the general thermodynamics part, and after that we will discuss the statistical thermodynamics. So the statistical thermodynamics here, 2 units are there. In statistical thermodynamics, 2 units are there. So in statistical thermodynamics is a separate type of thermodynamics. So that is a different type of thermodynamics from the So up to now we have discussed the general thermodynamics. Now we'll start the statistical thermodynamics. So the statistical thermodynamics is a separate type of thermodynamics. So you have not studied up to your graduation level, so that is a new type of thermodynamics. So we'll discuss. So we'll start the statistical thermodynamics from next class. Okay.
Okay, sir. Sir, can you please
Up to now,
papers?
hello. Up to
Hello?
now, the general thermodynamic parts are over. So all of you today go. All of you go through the general thermodynamics parts. If you have any doubt in any portion or in any derivation portion or in any numerical examples or any questions, you should ask tomorrow. Otherwise, you will start the statistical thermodynamics from tomorrow, because so for today there is no time is there. So this is a new type of thermodynamics you have not studied so in your graduation level, so that's why. So the statistical thermodynamics will continue from tomorrow. We will start tomorrow. Okay.
Okay, sir.
Okay, thank you, sir. Sir,
Okay,
can you
sir.
please
Thank you,
share
sir.
the previous year's question papers for physical chemistry?
So previous year question paper is with me now, but how can you okay, so I will put in that group. Okay.
Okay, sir. Sir, which group, sir?
Thank you, sir.
Okay, sir.
Actually, one group is there, one WhatsApp group created. Someone created one WhatsApp group yesterday. So I
Okay.
will put the questions on that group. Okay.
Okay, sir. Thank you, sir. Can I ask who has created the group?
Actually, this was the group created by the study center.
Yeah, so acha, then I am in that group. Okay, okay, the
Yeah.
same group.
Otherwise, you can
No,
download it
no,
from the website.
एक अलग ग्रुप है स्टूडेंट का
हाँ कल किया था ना, कल किसी ने किया था,
हाँ,
but I was
How
unable
to?
to join it.
chemistry jewels go ignore.
Are you in that group?
अभी अभी
हाँ हाँ
चैट में अपना नंबर शेयर कर दो, वो अपना मतलब ऐड कर देंगे वो।
अच्छा,
अभी इस चैट में ना मैसेज में अपना नंबर लिख दो।
yesterday I sent the number but they have not added me. Okay, I'll resend it then. Thank you.
अरे असाइनमेंट किए के सब लेखा आरंभ करलणी?